Kia ora and welcome to this video on question 2 of the 2020 School Calc exam. 3 parts to this question. The first one, a really neat algebraic problem, very short, elegant solution. 2b, we're looking at graph features, turning points and concavity, points of inflection. The function itself is quite a simple quotient, but when we have to differentiate it twice it gets a bit messy. And then the third question is a geometric proof that involves trig identities. Alrighty, question 2a. I'm going to show you a painful, tedious way of doing this problem, and then we'll go through the quicker way. I guess the idea of doing that is that you appreciate sometimes staring at a problem a little bit longer and thinking about your plan of attack rather than just diving in. So for the question, if we want to find the exact value of x to the 8 plus 1 over x to the 8, we don't actually need to find x to do this. But one of the ways of solving it could be to find out what x is. So given the information about x, we could solve this equation to find out what x is. If we times this whole equation through by x to the 4, or we make a substitution, u equals x to the 4, then we've got u plus 1 over u equals 7, which is equivalent to u squared minus 7u plus 1 equals 0. Okay, so that's timesing the whole thing through by u. If we solve this using the quadratic formula, we get 7 plus or minus 3 root 5 over 2. There was 45 under the square root, but I simplified the third down. So that's x to the 4. And it has 2 values. It turns out you can use either of the values. I checked both of them to see that they work in there. And that's because the problem is set up with the reciprocal in there as well. And so if we flip this expression upside down, we actually, it still works. Okay, and then the question says, well, let's find x to the 8 plus 1 over x to the 8. So x to the 8 plus 1 over x to the 8, I'm going to have to take this value of u and square it, and then reciprocate and square it. So like I said, you can take any of the 2 values, it doesn't really matter which one you do. So I'm going to take this value as my x to the 4 and I square it, and then I add the reciprocal squared. The first term there's got a 2 squared on the bottom, so it's going to be over 4, and the other one's got a 4 over something. 7 plus 3 root 5, when you square it, it simplifies to 94 plus 42 root 5. Okay, 7 squared is 49, 3 root 5 squared is 9 times 5, 45, and you add them together. 49 plus 45 is 94, and then you get 2 lots of 3 times 7 times root 5. And then we're going to get the same thing on the bottom here. And then that last term we just need to use conjugates to rationalize it. So times that one by 94 minus 42 root 5, top and bottom. The denominator becomes 16. It's a difference of 2 squares, and 94 squared take away 42 squared times 5 gives us 16 on the denominator. And then the numerator is 4 lots of 94 minus 42 root 5. Okay, and then when we put these together, notice that 4 over 16 there is just 1/4, So we've got the same thing there, just a conjugate. So when we add them, the irrational stuff disappears. So no surds in the answer, and we get 94 over 2, which is 47. So that's the final answer, and it was a bit tedious, but it worked. And nowhere did I use the calculator. So if I had have cheated and at this point here worked out what this was as a decimal, and then with that decimal substituted, oopsies, not that way, substituted into there and into there, I would have got 47 as an answer, or I would have got really, really close to 47 if the calculator did a little bit of rounding. But that would be it would be an invalid solution, because as soon as you have to reach for technology and you're not proving the intermediate steps of algebra, you're not going to get full marks. Alrighty, let's just look at the problem again, but from a different viewpoint. If we want to connect the information that's given to the information we need, hopefully you can see that by squaring the information given, we're going to get x to the 8 and 1 over x to the 8. So if we, so method 2, if you just take x to the 4 plus 1 over x to the 4, and we know that equals 7, if we square both sides of this, then expanding this is going to be x to the 8 plus 1 over x to the 8, but there's also the middle terms, x to the 4 times 1 over x to the 4 twice. So x to the 4 times 1 over x to the 4 is 1, we've got 2 lots of that, and that's 49, and then we just take away 2 from both sides, and our answer is the same as before. So it's a really, really short solution, very elegant, and it just pays to look at the information you're given and try and work out how it's connected. Okay, part B, we've got a function cos x over 2 plus sin x, and we're told just to look at the domain 0 to 2 pi. So all the x values within that range are valid. Any other x values we don't need to consider. And we're looking for the turning points and also the points of inflection, because we want to discuss concavity. So it's not a bad function, as I was saying in the prelude to the video. What is messy though is that second derivative, and so it pays to be real careful with pluses and minuses and simplifying things before you move on to the next step. Very, very easy to make a little minor error in this question, and it's one of those scholarship problems that it's based on your level 3 knowledge, so you should be able to get it right if you just take a little bit more time to make sure it's all accurate. So first up, differentiating once, use the quotient rule. So we diff the top times the bottom minus diff the bottom times the top, all divided by the bottom squared. And then you can see at the top there, this term minus sin x times sin x is negative sine squared, and this term minus cos x times cos x is minus cos squared. So we've actually got a sine squared plus cos squared term there with a minus in the front of it. And sine squared plus cos squared is equal to 1, so what we've actually got is minus 1 minus 2 sine x, all divided by 2 plus sine x. So that's our derivative. The first part asks us for stationary points. So we're going to make this equal to 0. That tells us that 2 sine x must equal 1. No, it doesn't. It tells us it needs to be equal to minus 1. Or sine x equals negative 1/2. And then the sine function on 0 to 2 pi looks like that. Minus 1/2 goes through here. So we're looking for this point here and that point there. If you, on the calculator, if you go x equals sine inverse of negative 1/2, I'm just going to check to see what that gives. It usually gives you an acute angle. It gives us minus 0.5235, which turns out to be pi over 6. So what it's doing there, that is minus pi over 6 on the calculator, it's giving the solution there. So to find the other two solutions, this one here will be 2 pi plus, minus pi over 6 plus 2 pi, because it's a whole period later, and then the solution in here is found by knowing where the minimum of the sine graph is. I'm just going to move this out of the way because it's going to get a bit messy. So that one there was minus pi over 6 plus 2 pi, which turns out to be 11 pi over 6. We know that the minimum occurs at 3 pi over 2. The difference between 3 pi over 2 and 11 pi over 6, 3 pi over 2 is 9 pi over 6. So this, by symmetry, the solution that's, oopsies, lost my sine graph. The solution that we want there, that's going to be 7 pi over 6. Or you cheat and you just make a graph of it on the graphics calculator and then work out what the decimals are as exact values. The question does ask us for exact values of x. So our two stationary points, turning points, x equals 7 pi over 6, x equals 11 pi over 6, and asks for the coordinates of them. So if we just have a look at the Desmos graph of it, there's our minus pi over 6, but we didn't want that one. That's our minimum there, 7 pi over 6, and our maximum 11 pi over 6. And 0.577 is actually 1 over root 3. But to find that, we just need to go back to the original function and find the y values. So finding the y values would go, first up, f of 7 pi over 6. It's going to be cosine of 7 pi over 6 divided by 2 plus sine of 7 pi over 6. Now we already know what sine of 7 pi over 6 is, okay, because sine of x was equal to minus 1/2, so that sine of 7 pi over 6 must be minus 1/2. And then cosine of 7 pi over 6 can be worked out as well. Or you have an upgraded calculator, but we get 1 over root 3 for that one. Sorry, negative 1 over root 3 for that one, and then f of 11 pi over 6 is equal to 1 over root 3. What you can do if you don't recognise the decimal is square it. On the calculator, if you square it, it gives you a third, so you know that the answer here is the square root of a third. Okay, second question asks us to describe the concavity. If we look at the graph from 0 to 2 pi, there's a point of inflection occurring at the x-axis at pi over 2, where the curve goes from being curved downwards to curved upwards, and then there's another point of inflection there. Let's just prove that, but obviously looking at the graph it makes it easier to understand. So we need a second derivative, and so I think if we start with the first derivative being really in its simplest form, there's a common factor of a minus that I can pull out the front of the at the front of the first derivative. And then that just sits there when I differentiate again. I'm going to have a minus. I want to diff the top, use the quotient rule again, so diff the top, which becomes 2 cos x times the bottom minus the derivative of the bottom times the top, all divided by the bottom thing squared. Oopsies. Oh gosh, it was a little while back, but we needed the bottom thing squared under that derivative. I did say it at the time, I just didn't do it. Okay, so what does that mean? Makes this thing squared. It's going to change the answer to the question. Needs to be a squared there. Okay, the derivative of the bottom is now not as easy. It's going to be using the chain rule for the derivative of the bottom, 2 lots of 2 plus sine x times the inner derivative cosine x, and then times the numerator, 1 plus 2 sine x. What did I say at the start about being real careful? Oops. And that one's going to be 2 plus sine x all to the 4, because we're going to square the denominator. Okay, we're going to pull out some common factors here. In the numerator, we've got 2 cos x in both of the terms. So I'm going to pull that out the front. Minus 2 cos x. The stuff in the brackets, the first term has 2 plus sine x all squared divided by 2 plus sine x all to the 4. So it's going to be 1 over 2 plus sine x squared. There's a minus. And then the 2 plus sine x cancels. So we cancel those with 2 underneath. And then that one's going to cancel off with one of the ones underneath and make it a 3. Just be careful when you're setting out your cancellation that the working still follows accurately. We've got 1 plus 2 sine x on the top. We've got 2 plus sine x cubed on the bottom. Okay, now points of inflection occur when there's a change in concavity. When we solve the second derivative equal to 0, we are trying to find those changes. They aren't necessarily points of inflection though. So if we are solving the second derivative equal to 0, one of the options is cos x equals 0, and that gives us pi over 2 and 3 pi over 2. Turns out that they are the answers that we want. But what we need to prove is that there's a change of concavity from to the left of pi over 2 to the right of pi over 2. And we'll do this on a number line in a sec. Now the other option is that we solve 1 over 2 plus sine x all squared equal to 1 plus 2 sine x all over 2 plus sine x all cubed, because if those two things are equal, then that second bracket, the big bracket, will be 0, and that's going to be 2 plus sine x equals 1 plus 2 sine x cross multiplication, and that gives us sine x equals negative 1, and sine x equals negative 1 at x equals 3 pi over 2. Remember that we're only looking between 0 and 2 pi. We've already got that answer though. So you could have made a big stuff up in the derivative, and actually you would have still got the right answers to the problem, because the cosine x factor was the only important factor there. That factor was the one generating the solutions. Okay, so lastly is to discuss the concavity, we need to reason about the sign of the concavity, the sign of the second derivative. So we go like y dash dash. Now we know at x equals pi over 2, we know that the second derivative is 0. That doesn't necessarily mean a point of inflection. And then 3 pi over 2 is another critical value. So we just need to think about to the left and to the right of the thing. So first up, all values of x are possible. Okay, the second derivative is defined for all values of x. It's a continuous curve. There's no asymptotes. And if you think about substituting any value of x into the second derivative, this thing's always positive. It's never 0. This thing's same likewise is never 0, because it's 2 plus sine x all cubed, and 2 plus sine x, the lowest that will get is 1, because the lowest sine x gets is minus 1. So we don't have any division by 0 or any issues with that. So we just need to test values. So I could say when x is 0, x equals 0, the second derivative, cosine of 0 is 1, so that term will disappear, or becomes 1. Sine x is 0, so that term disappears completely. And we end up getting minus 2 all times, let's just get the calculator out, minus 2 times a quarter minus an eighth gives us minus a quarter. So that's concave down. If we go back to the graph, it is concave down at 0, it's curving downwards. And then if you do that for other values of x, so we could choose between pi over 2 and 3 pi over 2, kind of makes sense to choose pi as the other value to test. We don't have to worry about any other values because there are only two positions where the second derivative is 0. So if we go pi and we substitute pi into this, sine of pi is 0, so all those terms that have crossed out are still crossed out, and cosine of pi is -1. So all you get is a sign change. It's going to be a quarter, and so on. So what we're going is it's going from concave down. Now it's concave up. And if you do another value like 2 pi gives you exactly the same value as 0 did. For all of the trig functions have a period of 2 pi, so you get back to -1/4 there. And we're back to concave down. Okay, so in summary, when x is between 0 and pi over 2, concave down. When x is between pi over 2, 3 pi over 2, concave up. Second derivative is positive, and then between 3 pi over 2 and 2 pi, concave down again. And then points of inflection. Have I found the coordinates of the points of inflection? Nope. So a point of inflection at pi over 2 is the x value, and I'll leave it up to you to check that the y value is 0. We saw that on the graph. And there's also a point of inflection at 3 pi over 2, 0. Cool. Not a bad problem, but quite easy to make mistakes, as you saw in my second derivative. Actually, it was the first derivative I stuffed up. Okay, last problem. We're given a shape, cyclic quadrilateral, and we're told it's symmetrical, and then we've got to prove a over b equals that quantity there, and then calculate the magnitude of theta if b is a over root 3. Okay. Again, I'm going to show you two methods to solving this. Number one is if you recognize, because this side here is a and this side here is b, it's symmetrical, then what we've got here are right angle triangles. Now, opposite angles in a cyclic quadrilateral add to 180 degrees, and because of the symmetry that we've got there, they must both be 90, and AC must be a diameter. So if you recognize that, then going back to the problem, it gave us the angle of theta being the angle at the top. So this will be theta over 2. And then from that we've got A over B is equal to, what angle do we want there? If we're using the theta over 2 one, then A is the adjacent side and B is the opposite side. So we've got adjacent over opposite, which is the reciprocal of tan. So it's cotan theta over 2. that is cos theta over 2 divided by sine of theta over 2. We've got half angles. So if we go to the formula sheet, I'm just going to find, because I don't have one on me. You get double angle formulas. Sine 2 theta is 2 sine theta cos theta, and then you've got different options for the cosine one. One of them is 2 cos squared theta minus 1, and the other one is 1 minus 2 sine squared theta. So if we want half angles, we want to half that angle there, make that theta, then this one will be theta over 2. And likewise for the top one, if we want to make 2 theta, only theta, then it's going to be theta over 2 there and theta over 2 there. That's the half angle formula. And then to mess around with this top thing, we rearranged this equation. So it's cos theta plus 1 all divided by 2 square rooted. I've spotted an easy way of doing this. If I go cos theta plus 1 all over 2, and then I divide by the sine version, 1 minus cos theta all over 2 square rooted, I can simplify that. But an easy way to do it is to times the top and bottom of this expression by cos theta over 2. Actually, no, what do we want? What are we aiming for? We're aiming for 1 plus cos theta all divided by sine theta. Okay. So if I times this expression that I've got by 2, and then also by cos theta over 2, top and bottom. Okay, so I've just times by 1. And I can see that that denominator now is just sine of theta. And the numerator is 2 cos squared theta over 2, which is cosine theta plus 1. And I've got the proof. How neat. Now, I've got a little bit of an omission to make. When I first did this problem, I didn't notice the 90-degree angles, so I didn't think we could use right angle trig. So what I did, and it works, but it's a lot more tedious, is I split the shape across there, found this length BD, and I found 2 different expressions for it using the cosine rule. So if I call this x, actually, I'm going to call it c. The cosine rule tells us that c squared is equal to a squared plus b squared minus 2ab cos capital C, so the angle. So for the first triangle, the top one, I've got c squared is a squared plus a squared, because the sides are both a and a, minus 2a squared cos of theta. Okay, so that's one relationship. And then if I use the bottom triangle, I get c squared is b squared plus b squared minus 2b squared cos, and then this angle down here will be pi minus, well, if we're in radians it's pi, but if we're in degrees it's 180 minus theta, because opposite angles of a side quad. So I get 180 minus theta there. Now, I don't want the c part in this expression. I want a relationship between a and b. So if I just have a quick look at a trig graph. If I've got cos of, I've got to change to radians here, cos of pi minus x, that gives me a negative cosine graph. So the pi is a shift and then the minus is a flip across the y-axis. So if that's a negative cosine graph, then I can change this to theta and change that to a plus. Okay, and then subtracting these equations to eliminate the c. So I've got 0, checking, this is a squared times, no, it's 2a squared times 1 minus cos theta, and this one's 2b squared times 1 plus cos theta. So if I subtract the equations, it will work, but I can also divide equations. In simultaneous equations, I could divide them. So left hand side, equation 1 divided by equation 2 is 1 equals 2a squared 1 minus cos theta over 2b squared 1 minus 1 plus cos theta. Cancel the 2's, and I wanted a over b. So I've got a squared over b squared. If I cross multiply this thing, equals 1 plus cos theta over 1 minus cos theta, which doesn't look like what we're trying to achieve here. Remember that we wanted cos theta plus 1 in the numerator, which we've got, but we've got that extra term in the denominator. So what I do is times by the conjugate of the denominator, and I've got 1 plus cos theta all squared in the numerator, and then on the denominator I've got 1 minus cos squared, the difference of two squares, which we know is equal to sine squared. And then that's a squared over b squared, so a over b is the square root of that. Oh, don't need to write it, just go 1 plus cos theta over sine theta. I don't need to worry about absolute values there because of the fact we know that theta is between, from the diagram it looks like it's an obtuse angle. Yeah, cool, it's a over b. A over b is a positive number because it's a ratio of two sides. Alrighty, now the last part of the thing says if b is equal to a over root 3. So if b equals a over root 3, or a over b is equal to root 3, then we use the equation that we've already proven. So we could go root 3 is equal to 1 plus cos theta over sine theta. Like, we could solve that, but that's going to require us to solve a quadratic equation, because I'd be going cross multiplying this, I'd be squaring both sides. So I've got 3 sine squared theta, it's 1 plus 2 cos theta plus cos squared, and then I'd be switching the sine squared to 1 minus cos squared, and then I'd be rearranging this, 4 cos squared plus 2 cos theta minus 3 equals 0. I'm just going to check, but that's it. And if I let u equal cos theta, does this actually factorize? Let's have a look. Polynomial, just grabbing my graphics calculator here. Nope. What's a over be b equals a over root 3. So just checking that I'm doing this right. Yep. A over b root 3. Cross multiply, expand it. Minus cos squared theta. Oh, because it's not minus 3, it's minus 2. Okay, I bet you that factorizes now. Yep. So I don't need to make u equal cos theta because the roots are very easy once you've got it on the calculator. It factorizes to, well, we can divide everything by 2. And then factor this. 2 cos theta minus 1 cos theta plus 1. Remember when you square both sides of an equation, sometimes you bring in a solution that's not actually a solution. So this was telling us that cos theta plus 1 equals 0 is a possibility, but we know it's not. Cos theta plus 1 doesn't equal 0, because the original problem therefore would be 0 over sine theta. So it must mean that cos theta equals a half. And cos theta equals a half is an angle of 60 degrees. Okay, so at the moment the picture is drawn way different, because what we've got there is a over b equals root 3, which would mean that a is bigger than b, but at the moment it's drawn with an obtuse angle and b is bigger than a. Now that is a way of solving it. It involves a quadratic equation involving a trig expression, but if you just go right back to the first equation we had, which was that what was it? A over b equals cotan of theta over 2. Which is the same as b over a equals tan of theta over 2. And b over a for this question is 1 over root 3. If you just take the inverse tan of both sides of that equation, you'll get theta over 2 is the inverse tan of 1 over root 3. Now that's, it turns out that when you do that on the calculator, you get exactly the answer that you want. So that comes out to be 30 degrees, and therefore theta is equal to 60 degrees. Much easier to solve that equation because there's only one trig ratio in it. Okay, catch you in the next video.